Welcome to 3.5 exponential and logarithmic models. Logarithms and exponentials occur oftentimes in science type problems. They investment problems. There are just a lot of real world examples where these models fit data very, very well. There may never be a true, for instance, bell curve of a sample population. You know, like what's the, if we take the heights of all the students in the school, we would probably get some type of bell curve where we have very, very few students, say, under 4'10", and very, very few students over 6'6", and most of our students fit in this population, maybe let's just say we're talking males for the purpose of this, since I went to 6'6" on this. Let's just say most of the population fits in about a 5'9" range, but the data might not truly fit a bell curve, but there may be points around here. Here's the heights of all these different students, and a bell curve can be used to model that and make predictions. But there's a lot of real-world examples that use these following curves. Now, some of these we should be familiar with. We should recognize this is likely an exponential curve. That's our example one. That's our exponential growth. An exponential decay would be our e to the negative x. We could have a multiplier in front of that. But anyway, this would be like a decaying population, an exponentially growing population or investment. Or the value of our truck is going down, but it's never going to get below zero. This logistic model would be maybe a pretty good example of a population growth. Let's say you get a pair of guppies, put them in a tank, and the population just starts exploding, but the tank's only so big, so there's a carrying capacity on the tank. So the growth slows down and eventually would level off. And then we should probably recognize these have the appearance of logarithmic with an asymptote 0. Note, if we put 0 in here for ln, we get an asymptote. If I put 1 in, ln of 1, the exponent that turns e into 1 is 0, and therefore we have this point. So we can kind of pinpoint that, hey, this might be a logarithmic graph that's moved up 1. You do not need to memorize these, although we should recognize some things about our logarithmic graphs and exponentials. But just for maybe planting a seed for future, these are very, very common graphs to use. Those of you that are going to be moving into a statistics environment, and probably most people in this class, I almost venture to say everybody will take a statistics course at some time in their college career, if not high school. This Gaussian model, what gives us this bell curve. It doesn't have to be 4e to the negative x squared, but we get that negative x squared term up here. That's pretty much a dead giveaway that we may be dealing with a statistical bell curve type problem. So anyway, let's assume we didn't just look at any of that. And we see, wow, we've never dealt with this kind of a curve before. This sort of looks logarithmic. Looks like we have an asymptote. This looks exponential. This looks logarithmic. Perhaps there's an asymptote here at -1. This looks exponential, but upside down, or backwards, I should say. This one, we haven't really dealt with, but looks like 0 is ultimately end model behavior to the left, and 4 looks like it's kind of a player. So this first one, I might just say, well, two things I notice. It's always positive, and it reaches its peak at 2. You might notice something about the 0 here, but I'm really focusing in on what I would consider that we probably have a Mivox value of 2. So we look over our equations. 2 is not particularly interesting. 2 is not particularly interesting here. It makes this 4. 2 is kind of interesting here. 2 is when we get the smallest negative number we can get. See, this is going to be a negative. This inside of here is going to be positive, but the smallest we're going to get, the smallest negative number we're going to get eventually is when we put in 2. 2 is not particularly interesting, and 2 is not particularly interesting. So I would venture to guess that this is A. B, I think logarithmic, but I definitely know that -2, or I definitely suspect at least that -2 might be of importance on this, as this graph just seems to die out at -2 and chase along what appears to probably be an asymptotal path. So let's see. -2, not particularly interesting. Nope. Yes, it is. No, and no. So I would venture to guess that this one's B. let's see, C, we notice this is probably exponential. It's getting big really fast. I also notice that 0 goes through 2. So if I put in 0 here for x, I get e to the 0th 2. If I put in 0 here, I get e to the 0th. That's 1 times 6. If I put in 0 here, ln 1, nope. If I put in 0 here, I get 4 on 1, 2. Oh, there's another 2. So now it's just a decision time there. But I notice here, here's f. Here's a 2 when x is 0 as well. So when x is 0, this is of interest to me, and this one's of interest to me. But we do know this is an exponential, so this is C. I believe probably. Notice I put in 0. I get e to the 0, 1 plus 1. 4 divided by 2 is 2. Look what happens when I put in a huge value for x. I get e to a huge negative value, which is basically 0. 4 on 1 plus 0 is 4. Eventually, this thing looks like it's leveling off at 4. How about a huge negative value here for x? I get e to a huge positive value. 4 divided by 1 plus a huge positive is 4 divided by a huge positive, which wants to approach 0. So as we move to the left, we're trying to approach 0 over here. So that one is F for sure. 3 different ways we kind of determine that. Okay, then D looks logarithmic. Looks like -1 is of interest to us, and there we go. And E looks exponential, but backwards from what we're used to with exponential. There's exponential and backwards. Just for safety check here, put in 0, get out 6. Put in 0, get e to the 0th, 1 times 6, 6. Okay, so even without knowing necessarily that this is the kind of thing we're looking for here, we got some pretty good approaches based on things that we've done in the past investigating curves. Okay, and now some of the best problems maybe in the book for the masses are just these investment problems, so we just get a feel for handling money, making investments. Here we have complete the table for a savings account in which interest is compounded continuously. Continuous compounding. The amount we end up with equals, maybe I'll put it down here. The amount we end up with equals principal times e to the RT. That is really just a standard exponential growth problem. There's going to be others where we're going to use the same formula. It's just that instead of A and P, the amount we end up with equals the principal. It might be the amount at time t equals the initial amount. But this is always what we start with. This is what we end with. And this rate and time are going to be given, or maybe we're going to search to find those. Anyway, we have an initial investment of $2,000, an annual rate of 2%. So right now I can go e to the 0.02. That's our rate. We're going to be looking for the time, so I'm going to put in t here for it to double. The time for it to double, the 2,000 would become 4,000. Now, to be honest, I wouldn't even need to know that that's $2,000 here. It could just say an investment at 2%, how long does it take to double? And I could just put $1 here and $2 there. Because my first step, I'm now solving an equation with a variable in the exponent. I need to isolate the exponential factor. So I'm going to divide away 2,000, and I get 2 equals e to the 0.02t. And now that it's isolated, now I can take logarithm of both sides, and I'm most certainly going to use ln since we're base e here. ln2 equals ln, or log base e of e to the 0.02t. So ln2 equals, we could either do this, say this thing is the exponent that turns e into e to the 0.02t, or we could bring the 0.02t out in front, times ln e, and then hopefully we recognize ln e as 1. This is the exponent that turns e into e. So I get ln2 equals 0.02, 02t, or t equals ln 2 divided by 0.02. Now there's our exact answer, but of course that doesn't maybe necessarily have a whole lot of meaning to us, and as mathematicians maybe it does have some meaning to us, but certainly the general population not so much. So let's second clear, let's second quit, and clear this, and let's go ahead and find that value. Just trying to get a nice compromise here. So I'm going to go second, nope, not second, just plain old ln 2 divided by 0.02, and I get 34.657. So equals 34.657, and that of course would be years. Now, one thing I want to tell you, when you're working on these exponential problems and these logarithmic problems, typically if you make an error along the way, your final answer is just going to be ridiculous. For instance, if I got an answer like 0.316, well, a $2,000 investment is not going to double in 0.316 years. It's going to take a while. I mean, if it was just plain old simple interest, 2%, it would take 50 years to double. Well, this is compounded continuously, so it's going to be a fair amount faster than 50, but it's not going to be 72 million years. Those are the kind of errors you get when you make mistakes along the way on these types of problems. Usually, you're probably not going to make a mistake along the way and come up with an answer like 36.312 years. It's going to be something dramatic in most cases. All right, so that's time to double, and I definitely did not allow room for myself on this, so I'm going to come back up, and I apologize. Should have warned you ahead of time to write smaller than I am on your note sheet, but I'm going to come back in here and do amount after 10 years. So I'm going to say A10 equals 2,000 e to the, this is an easier one. This is actually straightforward. I probably could squeeze it in there. E to the 0.02 times 10. And if it doubled in 34 years, it's not going to double in 10 years, but we're still going to have a fair amount more. But it's going to be less than 34,000 by a fair amount. So that is straight calculator problem now. So let's go ahead and find that one. I get 2,000. That's a little bright. I think you can see that though off to the side anyway. Times second ln e to the 0.02 times 10. And we get $2,442.81. Definitely an easier problem where we don't have to do any equation solving there because our unknown was already isolated. Okay, I'll do better on spacing on this one. So here we don't know our initial amount. We do know our amount after 10 years. So we end up with 2,500. We start with unknown e to the r 0.035, and that took 10 years times 10. So this is pretty straightforward here. Our principal must equal 2,500 divided by 0.035 times 10. So our principal is approximately, let's see where we're at here, 2,500 divided by all of 0.035 times 10. And we get 7142.86. And now we want to know the time to double. So our initial investment was 7142.86. We'd need that to turn into what? 14,285.72, I think. Double that. Or I could just say, well, I'm going to you might be investing that. I'm only going to invest $1. It's going to take just as long for mine to double as it is yours. So I want to end up with $2. If I start with $1, e to the 0.035 times the amount of time. And there's our unknown. So we need to solve for that. ln 2 equals ln e to the 0.035t. ln2 equals, this is the exponent that turns e into e to the 0.035t. This is 0.035t. So t is ln2 divided by 0.035. Let's see if that answer makes some kind of sense to us. So I'll make it so it's seeable again here. So we've got ln2 divided by 0.035, which is the exact answer. Sorry about this. We have a little technical difficulty here. Try again. So there's the exact answer. If we want the approximation, which in this real world problem we probably do, 19.804 years. And that seems somewhat reasonable. Remember, for 2% interest, back on problem 14, it took almost 35 years. 3.5 is considerably greater than 2% relative. And of course, our money doubles quite a bit sooner. This seems at least somewhat reasonable. Okay. Now, before we talk about the next problems, which are in your note pack right here, they're talking half-lives, and I want to explain half-life in terms that I think we can all get our head around here. So let's say we have a stink bomb, and it says on the package that it has a half-life of 10 minutes, meaning that every 10 minutes the level of smell would be cut in half. And assuming we have a smellometer, if the initial reading of a stink bomb is 72 on the smellometer, how long would it take to reduce to 5? Well, let's just go approximate here. I know if it starts at 72, and that's at time equals 0, so here's our smellometer. It's going to be 36 in 10 minutes, and then it's going to be 18 10 minutes later, and then it's going to cut in half again to 9 10 minutes later, and then it's going to cut in half to 4.5 10 minutes later. It's going to take about 40 minutes. Well, maybe we need a more exact answer than that. Maybe we need to know when is it going to be exactly 5, not when can I come back into the room because I can tolerate the smell. 40 minutes would be good because it's going to be below what we could tolerate, I guess. So it would be somewhat comfortable, I suppose. So what are we really doing? We're taking that initial amount, multiplying it by a half, and then by a half, and then by a half, and then by a half. We're taking the initial amount, I'm going to say smell at time 0. Smell at time t equals the smell at time 0 times, I'm not multiplying by e here, I'm continually multiplying by 1/2. And continually multiplying by 1/2 implies times 1/2, times 1/2, times 1/2. Implies 1/2 to an exponent. This would be 72 times 1/2 to the first, 72 times 1/2 to the second, to the third, to the fourth. But let's say we only allow the time to go 3 minutes. I don't get to multiply by a full 1/2. After 3 minutes. I'm going to be somewhere less than 72, greater than 36. I don't get to multiply by a full 1/2. I only get to multiply by 3/10 of it. Or if I wanted to go 17 minutes, well, first, if I just allow it to go 10 minutes, I multiply by a full 10 minutes. Or excuse me, I multiply by a full 1/2. If I allow it to go 20 minutes, 20 divided by 10, I multiply by a half twice. If I allow it to go 30 minutes, I multiply by a half 3 times. If I allow it to go 17 minutes, I'm going to multiply by a half 1.7 times. So our half-life formula makes sense to me. The smell at time t equals the initial smell times 1/2 to the, what I put in the bottom here is the actual half-life, and what I put in the top is the actual time. For 30 minutes, we multiplied by 1/2 once, twice, 3 times, 30 divided by 10. For 17 minutes, we'd multiply by 17 divided by 10 here. So here's what I want. I want my smellometer to reduce to 5. The initial reading was 72. I started multiplying by 1/2. How many times how much time passed? I don't know. But for every 10 minutes, I'm going to divide that and get another increment of a full 1/2. Now here is a super common mistake people make. They say, okay, well this is 5 equals 36 times. No, exponents only work on that base. So I need to isolate this. So I'm going to have 5 on 72 equals 1/2 to the t on 10, and now I have an exponential isolated, and I'm just going to take ln of both sides. You could take logarithm. In theory, you could take log base 5 on 72, which would sort of make some sense here, but I'm just going to do it this way. So that gives me ln, I didn't want to do that, ln 5 on 72 equals t on 10, pull it out in front, the exponent, ln 1/2. To get t alone, I need to multiply 10 ln 5 on 72, and I need to divide away the ln 1/2. Now I'm hoping that our answer, remember where we were here, we think our answer is going to be pretty close to 40 minutes. In fact, maybe just a little bit less than 40. Let's see how we did on this. So let's get another good view of this. Try again on my, to get a nice compromise here where we can see everything. And let's run that one through here. So I get 10 ln 5 divided by 72 all divided by ln 1/2. And there we go, 38 point, looks like we could agree on 38.480. And that's very reasonable, considering we expected it to be 40 would get us to a smellometer of 4.5. So we need something slightly less than 40 to get down to 5. And there we have it. Okay, so there's our introduction to half-life, a formula that I hope we can make some sense out of. And here we have a half-life problem, and I'm going to repeat that formula. It's going to be the amount at time t, in the past it was smell, but amount at time t, not 2, equals the initial amount times 1/2 to the time divided by the actual half-life. So we have this 239 Pu, it's an isotope, and it has a half-life of 20. This might be like carbon dating, you know, figuring out how old a dinosaur bone is. We assume it has a half-life of 24,100 years. That's almost certainly rounded. I doubt we've stuck around 24,100 years to know that it's exactly half. So there's a lot of study and theory that goes into that. But we don't know the initial quantity. This is good news. Amount at time t equals, we start with 24,100. We start multiplying by halves. How many halves do we multiply by? Oh, wait a minute. Don't know the initial quantity. Mistake. We know what we have after 1,000 years. So after 1,000 years, we end up with 0.4. That was totally wrong. And we don't know what we started with, so that's amount at time 0. You can just use A there if you'd like. Multiply by 1/2. We do know it took 1,000 years, and we do know the half-life is 24,100. And we just need to solve for A naught, or the initial amount. So A naught equals, I don't have to use a logarithm, I don't have a variable in the exponent, I just want to solve for this. So it equals 0.4, and we need to divide away 1/2 to the 1,000 on 24,100. And there's our exact answer. Our approximate answer is, let's see, 0.4, going to be too bright. I think maybe you can see that. 0.4 divided by all of, I'm just going to go 0.5 raised to the 1,000 divided by 24,100. And let's see if we get an answer that at least seems reasonable here. And we get 0.41167. So I'm going to go 0.412. So we get 0.412. That would be grams. Now that's not much bigger than this. And we know that what we started with reduced because so it did reduce, but it didn't reduce very much. Is that reasonable? Well, it takes 24,000 years for it to get cut in half. So we went from 0.412 down to 4. It certainly didn't get cut in half, but it shouldn't really come that close to getting cut in half. But if this was, we might get a crazy answer like, oh, we started with 96 grams. Yeah, there's no way. We're only going through the tiniest bit of a half-life, so we should have only started with a tiny little bit more than the 0.4. The answer is reasonable. Okay, very similar problem. Be a great one for you to try if you want to pause here and come back and check. Here we go. Hopefully you gave this one a shot. Still got a chance. Pause it, try it. Welcome back again. So the amount after 1,000 years is 0.1 equals, how much did we start with? Don't know. Amount at times 0 times 1/2 to the, we got a different radioactive isotope here, number 238. It has a much different half-life. So its half-life 87.74. How long did it go? It took 1,000 years to do that. Butchered that a little bit. So it's 1,000 divided by, that's how many half-lives we've gone through. 1,000 divided by 87.74. Hope that makes sense. So A naught is 0.1 divided by 0.5 or 1/2 to the 1,000 divided by 87.74. Let's do it this way. So I get 0.1 divided by all of 0.5, 1/2 raised to the 1,000 divided by 87.74. And we get approximately 269.732 years. And let's see, does that make sense? Oh, that's not years. That's grams. Okay, well, 87. Yeah, we need to have quite a few here. We need to start with a fair amount initial quantity of grams because we get cut down all the way down to 1. So this got cut in half and cut in half and cut in half and cut in half. Well, it's going to get cut in half quite a few times from here to here. So at least seems somewhat plausible. You could go through the cutting this in half a whole bunch of times, or take 1,000 divided by 87, and that's how many times you cut it in half. And I think we're going to believe if we started with that, we might actually end there. Okay, so here's an exponential. Take a look at this formula. This is a lot like our formula that we were dealing with when we had A equals P e to the RT. We got an amount, we got a variable, e to the, we got a variable, and t is our x value. Okay, the key to this problem is this point right here. I'm going to use amount at time t equals initial amount e to the RT. It's the same formula. And you may not use this, but it's pretty applicable to most problems like this. So the amount after certain time, well, after time is 0, the amount we have is 1. So 1 equals A naught e to the R times t is 0. I can put that point in right here. Now, the book's going to say use this formula. So I'm going to go and use this formula and show you why it's the same thing. Y equals A e to the bx. We got a y value of 1, but that's what we started with. At time 0, we started with 1. We got a y value at 0. a e to the b. I don't know what b is. That's truthfully our r value. The x value is 0. So we get 1 equals a. Oh, a is what we started with. A is 1. We already knew that that value was 1. Well, that's good to know. So that's going to be helpful for us. Like in 34, we start with 5. A is 5. At time 0, we start with 5. So our formula becomes amount at time t equals 1 times e to the rt. I just need to figure out what r is. I've got another point. Or in this case, y equals 1 e to the b times x. I've got my a value. I've got another y value. 5 equals e to the b times x when the x value is 4. ln 5 equals ln e to the 4b. But this is the exponent that turns e into e to the 4b. This is 4b equals ln 5, and b is ln 5 divided by 4. Our exact answer for our model then is y equals 1, you don't need the 1 of course, e to the ln 5 on 4 times x. I just put those values for a and b right in there. Now the back of the book may have that rounded, but that's our exact value rather than rounded.